In this video, we will talk about session 9.5, power series and the interval of convergence. So before we start, we first introduce the definition of a power series. A power series about x is a sum of constant times powers of x minus a, that is this kind of form. C0 plus C1 times S minus A plus C2 times S minus A to power n. And in sigma notation, it's sigma Cn times S minus A to power n, and n from 0 to infinity. We think of A as a constant. So for any fixed x, the power series is a series of numbers like those in session 9.3. So to illustrate the convergence of a power series, we also consider the partial sums. In this case, the partial sums as nx is C0 plus C1 s minus A, then plus C2 s minus A squared, then plus Cn s minus A to n. So in this case, the partial sums are polynomials. So for a fixed value, of x, if this sequence of partial sums converges to a limit s, then we see that the power series converges to s for this value of x. So if we have the limit of Snx, Sn goes to infinity, is s, then we see that the power series converges to s for these values of x. So now we look at an example. We look at this power series, sigma s minus 1 to power n over 2 to power n, and from 0 to infinity. So for this power series, we can write it as s minus 1 divided by 2 to power n. We see that each different value of x gives us a different geometric series. The series converges if the ratio x minus 1 over 2 between successive terms is less than 1 in absolute value. So if this absolute value less than 1, that is absolute value of s minus 1 less than 2. So s minus 1 less than 2 greater than negative 2. So we have x less than 3 greater than negative 1. So the series convergence between negative 1 and 3. So we have the series convergence if x greater than negative 1 less than 3. And the series divergence if the absolute value of s minus 1 over 2 greater than or equal to 1. So s minus 1 greater than or equal to 2. So we get x less than or equal to negative 1 or x greater than or equal to 3. So we have the series divergence if x less than or equal to negative 1 or x greater than or equal to 3. So if we draw it in the real number line, this is 1, 0, 2, 3, -1. So we have it the convergence if x greater than -1 less than 3, and divergence if x less than -1 or greater than equal to 3. So this example illustrates a general phenomenon about the power series, namely that if x is within a certain distance either side of A, so A is 1, then the power series converges. This distance is called the radius of convergence, R. This is the radius of convergence. So for this case, the radius of convergence is 2. It's 2. So there are 3 possibilities which can occur for the radius of convergence. So one case is the series convergence only for x is A. In this case, the radius of convergence is defined to be 0, I is 0. So the second case, there exists r greater than 0 less than infinity, called the radius of convergence. Such that the series convergence for the absolute value as minus A less than R, and the divergence for the absolute value as minus A greater than R. The series convergence for, so the third case is the series convergence for all values of x. In this case, the radius of convergence is defined to be infinity. Note that in the second case, r between 0 and less than infinity, we know the series convergence for x minus A absolute value less than R, and divergence for the absolute value of x minus A is greater than R. We need to check the convergence of the series at the 2 endpoints A minus R and A plus R separately. So if we also draw it on the real line, so this is the center A, and here is A minus R, here is A plus R. Then from here to here, this is called the interval of convergence. And this R is this part, is this distance. R is this distance. So this part is the series divergence. If x less than A minus R, the series also diverges. So the interval A minus R, A plus R, together with those endpoints A minus R, A plus R, if any, at which we have convergence, together gives us the interval of convergence of the power series. So we need to deal with these 2 endpoints separately. So for the last example we did, we know its radius of convergence is 2, and the interval of convergence is from -1 to 3, and the open interval. So to find the radius of convergence, we have a test which is very useful. It's called the ratio test, also the ratio test. So we have the following test method for computing radius of convergence. So to calculate the radius of convergence, R for the power series use the ratio test with an is Cn x minus a to power n. So if we have the limit, that's the value an minus 1 over that's the value an, n goes to infinity. If this limit is infinity, then R, the radius of convergence is 0. If the limit is 0, then the radius of convergence is infinity. If the limit is k times the absolute value x minus a, where k is finite and non-zero, then R is 1 over k. This is a method for computing radius of convergence. Now we look at an example. Determine the radius of convergence. Of the series s minus 1 over 3 minus s minus 1 squared 2 times 3 squared plus and plus negative 1 n minus 1 s minus 1 to power n over n times 3 to power n. So for this series, we will use this method. We use the ratio test with an as this one, then do the ratio. So for this series, an is this one, right? So it's negative 1 n minus 1 over n times 3n s minus 1 to power n. So an minus 1 divided by the absolute value. So this is negative 1 n minus 1 s minus 1 power n times 3n, an minus 1. So it's n plus 1, n plus 1, 3n plus 1. Right, this absolute value then divided by an as the value. Simplify, we get this is s minus 1 n plus 1 divided by n plus 1, 3n plus 1, then times n times 3n over s minus 1n. So s minus 1 power n, this is the absolute value. Here you have the absolute value. Absolute value. To simplify again, we get the absolute value as minus 1n, then 3n cancel, get n over 3n plus 1. So this is the ratio. So at n goes to infinity, is equal to limit n goes to infinity s minus 1 times n over 3n plus 1. So this is s minus 1 over 3. So from here we get k is 1/3 in this theorem. This k is 1/3. K is 1/3. So the radius of convergence is r is 1 over k. So it's 1 over 1/3. It's 3. So the power series convergence for that's the value x minus 1 less than 3, and the divergence for that's the value of s minus 1 greater than 3. So the series convergence for x greater than -2 less than 4. So next, so we find the radius of convergence is 3. So next we go to determine the interval of convergence. So from this example, we get the interval, the series convergence for x greater than -4 greater than -2 less than 4, and the divergence for x less than -2 or x greater than 4. We needed to determine whether it converges at the endpoints of the interval of convergence to get the interval of convergence of this theorem. That is, we needed to deal with these two endpoints. So at x is 4, we have the series. If x is 4, this series becomes as is 4, so the first term is 1/3. X is 4, first term is 1. So as is 4, we have the series 1 minus 1/2 plus 1/3 minus 1/4, then plus -1 and minus 1 over n. So you see this is an alternating series. With an is 1 over n. So by the alternating series test, we have an minus 1, and this is 1 over n plus 1. So it's less than 1 over n. This is an. And the limit of n goes to infinity is limit 1 over n and go to infinity, it's 0. So the terms decreasing and the limit is 0. So by the alternating series test, it converges. This is at the endpoint x is 4. At x is -2, we have the series -1 minus 1/2 minus 1/3 minus 1/4 minus 1 over n. This is the negative of the harmonic series, so it diverges. Therefore, the interval of convergence is x greater than -2 less than or equal to -4. -4 is included, but the left endpoint is not included, because at x is -2, it diverges. So we get the radius of convergence is 3, and we also get the interval of convergence of the series is from -2 to -4, and the -4 is included, but -2 is not included.